Well, welcome everybody. I'm so pleased to see you all here from so many different diverse backgrounds. Really pleased to invite and introduce Debbie Coen to speak to us. She is a professor of history of science and medicine, and also at the moment I think chair of the Department of History of Science and Medicine, and involved in the Yale Humanities Initiative. She came to Yale from Columbia, where she was teaching for some time, and has a BA in physics, which I think is very, very impressive, from Harvard, and an MPhil in the history of science and philosophy of science from Cambridge. Her work focuses on trying to understand the modern physical and environmental sciences and how they have changed and how we describe and understand the world around us. At Yale, she is going to be able to enjoy having next year off with one of the Mellon Fellowships, is that right? To be able to take classes and to learn a little bit more about the physical and the social sciences around climate change. I think it's a really exciting opportunity for us to get to know Debbie and draw her into some of the work we're doing here. One of her interests is how scientists cope with uncertainty. Her first book is Vienna in the Age of Uncertainty. It won the Susan Abram Prize from the University of Chicago Press and several other prizes as well. She most recently published a book in 2013 on earthquake observers, disaster science from Lisbon to Richter, and has a book coming out, I believe, some point this year, titled Climate in Motion, Science, Empire, and the Problem of Scale. It would be the first study that looks at the science of climate dynamics before the computer age when we were generating models of climate change. So I'm awfully excited to have Debbie here and hoping we could do some really exciting collaborations in the years to come. So welcome.
Thanks so much, Amity, and thanks so much for this invitation. So I'm going to talk a little bit about my forthcoming book. And I just want to start by pointing out that many of the questions that climate change raises today, so questions about environmental and social justice, about the rights of future generations, about the relationship between science and traditional knowledge, are historical questions, that is, questions about how things came to be the way they are. And the notion of the Anthropocene posits humanity not simply as the first species to have changed the conditions of life on Earth, but that would be bacteria that injected oxygen into the atmosphere, but the first species to have done so consciously. This consciously, though, has been, of course, an unstable mix of knowing and not knowing the consequences of our actions. Hence, the question of how we know is key. And the methods of my own field, I think, history of science, are essential. And yet, when we talk about the historical origins of scientific knowledge of climate change, we tend to turn back no more than 70 years or so. We speak about the history of the science as if it had developed entirely in the United States after World War II. Earlier climate science, often called climatology, is frequently dismissed as a hodgepodge of folklore and superstition and mindless empiricism. In fact, our most comprehensive history of climate science to date, which is Spencer Weirt's discovery of global warming, which is excellent in many ways, insists that, quote, people who called themselves climatologists were mostly drudges who kept track of average seasonal temperatures, rainfall, and the like. And actually, as we're going to see in a bit, 19th century scientists anticipated that criticism. Now, it's not hard to see why a climate advocate like Spencer Weir would want to draw a sharp line between modern climate science and what came before, given the tactics of climate skeptics. But positing such a sharp rupture and locating it at World War II is not only historically inaccurate, I'm going to argue, but may also undermine our political goals. So, contrary to a recent New Yorker piece by Jill Lepore, modern climate science hardly sprang Athena-like from the heads of a few physicists toying with a computer in the aftermath of the Manhattan Project. Hidden in their models and equations was knowledge with roots stretching far around the world and back into antiquity. What I think we need now are capacious accounts of that process, histories that communicate to the public the depth and breadth of the foundations of our knowledge of climate change. Now, for most of human history, knowledge of climate had little in common with the science of prediction and control that would emerge from US weapons labs in the late 20th century. Instead, the roots of climate science lie largely in practical efforts to improve everyday life, from agriculture to public health to transportation and trade. Climate knowledge has come not only from scientists' studies of the atmosphere, but also from everyday experience with many aspects of nature that stand in mutual dependence with the atmosphere, such as vegetation and water supply and soil conditions. In the period I'll discuss today, the 1800s, climatological knowledge was being produced by experts of many stripes, including botanists, foresters, agricultural scientists, geologists, paleontologists, mining officials, medical geographers, pharmacists, balneologists, or spa doctors. 19th century botanists, for instance, referred to vegetation as an ideal climatic record, as, quote, everywhere the image of the local climate, while geologists recognized glaciers as the best possible, quote, climatic measuring instruments. What's more, professional scientists, as we're increasingly learning from historical research, often built on the traditional knowledge of those whose livelihoods depended on climate knowledge, such as farmers, sailors, and fishermen. So if climate science has such deep roots in history, we might wonder what, if anything, is distinctive about modern climate science? What makes modern climate science modern? The answer I propose in my forthcoming book is that modern climate science has managed to integrate phenomena of radically different dimensions, from the molecular to the planetary. This requires methods appropriate to each scale. Satellites are ideal for tracking hurricanes, for instance, but of little use for following the minute fluctuations in temperature and humidity that matter to the growth of a seedling. Just as important are methods of tracking interactions across scales, as in the relationship between cloud formation and the global radiative energy balance. Now, as the audience here well knows, scientists deal with the challenge of working across dimensions of space and time by means of what they call scale analysis, meaning that they estimate which are the significant phenomena for the purposes at hand and work with those to produce a reasonable approximation. So my new book, Climate in Motion, is essentially a history of this multi-scalar, multi-causal way of engaging with the world. That approach was unimaginable circa 1800, for reasons I'll explain in a moment. So how did a framework emerge for conceptualizing the multiple scales of the climate system? This is a critical question for the history of science, for the history of the Anthropocene, and one that I think I've been the first to pose. So circa 1800, scientists possessed rudimentary models of the planetary circulation of the atmosphere. Since the 18th century, this circulation had been understood to be driven by convection, as the sun warms air at the equator and causing it to rise and to sink at the poles. It was understood that the predominant winds were to the west in the northern hemisphere at the surface due to the rotation of the Earth. William Ferrel, a US physicist, introduced the major innovation of the 19th century. He realized that friction between the atmosphere and the Earth's surface would necessitate a mid-latitude circulation in the opposite sense. But Ferrel's model of the general circulation, which dominated until the early 20th century, treated disorderly motions at smaller scales, like cyclones and smaller eddies, as mere, quote, local disturbances superimposed on the mean current. Moreover, 19th century scientists had no way to integrate this global model with accumulating evidence of the fine-grained variability of climate across the surface of the Earth, as was being recorded by scientific explorers and agricultural and medical researchers around the world. This bifurcation was reflected in 19th century terminology. So, since ancient times, climate had signified the latitude-dependent effect of solar radiation, klima being the Greek word for angle of incidence. 3 climate zones neatly banded each hemisphere: frigid at the poles, temperate at mid-latitudes, and torrid at the equator. So late 19th century scientists contrasted the, quote, solar climate, meaning the distribution of heat to be expected on the basis of solar radiation and the known composition of the atmosphere, with the physical or terrestrial climate, meaning climate as modified by any number of factors, such as the shape of the Earth's surface, the distribution of land, water, and vegetation. Meanwhile, the temporal scale of climate was just as ambiguous as its spatial extent. The relevant timescales ranged from the seasonal, in the case of medical and agricultural climatology, to the geological, in the case of the new theory of the ice ages. Indeed, these temporal perspectives were proving impossible to reconcile. How could the evidence unearthed in the 1830s and 40s of an ancient ice age be squared with the apparent stability of the Earth's climate in historical times? If climate implies a time average state, it was not clear how long an interval was appropriate to its definition. So the study of climate circa 1800 proceeded at two radically different scales independently. Men of science typically opted to study climate either as a planetary physics or as a descriptive local geography. The science that bridged this gap was what I refer to as dynamic climatology, which can be defined as the application of the physics of heat and fluid motion to explain climatic conditions and their past and present distribution on the surface of the Earth. Dynamic climatology deserves a prominent place in the history of the Anthropocene, since it identified and began to address the challenges of conceptualizing interactions across scales of space and time, from the human to the planetary. I argue that it really marks the origins of modern climate science. And my new book argues further that we can't appreciate the full significance of dynamic climatology without understanding the historical context in which it developed. So dynamic climatology flourished in particular in the Habsburg Empire, which covered nearly 700,000 square kilometers of Central, Eastern, and Southern Europe in the 19th century. Because of its significance to the history of climate science and its relative obscurity today, I want to take some time now to introduce the environmental, socioeconomic, and political circumstances of this state circa 1800. Over the course of 7 centuries, through strategic marriages and battles, the Habsburg dynasty had acquired a motley yet contiguous set of kingdoms, duchies, and principalities. Extending through 9 degrees of longitude, the dynasty's lands were crisscrossed by mountains, one chain running east from the tall peaks of the Alps in the westernmost province of Vorarlberg down to the craggy towers of the Dinaric Alps, another rising to the east from the Bohemian Massif, and turning east into the Carpathians, a largely unmapped territory which separated off most of the empire from its most newly acquired territory, Galicia. Before the coming of the railways, the monarchy was largely dependent on its main riverway, the Danube, for transport. Its waters originated in melting glaciers in the Alps, flowed east through Vienna, Bratislava, and Budapest, into lands still controlled by the Ottomans in the 19th century, before emptying into the Black Sea. And across much of the Habsburg world, the grassy plains of the Hungarian steppe, the rocky, porous ground along the Adriatic, the high-altitude pastures of the Alps and Carpathians, agriculture was possible only during a brief season when adequate rainfall and mild temperatures prevailed. A swing of the climate could easily spell hunger. On the other hand, excess rainfall could trigger devastating floods along the Danube and its tributaries, especially in deforested areas, as well as rock slides in the mountains. In the marshy lands of the Carpathian Basin, 18th century attempts at water regulation had wreaked havoc with the ecosystem and threatened floodplain agriculture. Transport and communication across the Habsburgs' lands was also highly dependent on climate. During Europe's Little Ice Age, from roughly the 13th through the early 19th centuries, portions of the Danube often froze, and snow blocked certain mountain passes year-round. With the period of warming that set in circa 1860, baseline expectations from the past were not necessarily useful guides to the future. Now, the changes afoot in Central Europe in the 19th century were socioeconomic as well as environmental. The 19th century Habsburg Empire was a geographically extensive but semi-closed economic system, having been excluded from the German Zollverein in the 1830s. It was out of the race for overseas colonies and had minimal expectations of expansion to the southeast. Within its borders, capitalism was already beginning to produce its signature geography of unevenness. Between the end of the Napoleonic Wars and the stock market crash of 1873, industrialization transformed the distribution of production in the Habsburg lands. Regions of the monarchy that had once been economically self-sufficient were thrust into the role of imperial periphery, generating a flood of migrants to new industrial centers. After the crash, capital investments shifted to the periphery in order to take advantage of cheaper land, raw materials, and labor. In this context, climatology furnished advice for repurposing natural environments to suit the new economy. Possibilities included introducing new crops, beets for sugar, potatoes for spirits, launching a tourist industry, or, as you see here, building spas or sanatoriums to provide what was often called climatotherapy. At the same time, imperial climatologists were called on to adjudicate between proponents of development and those of conservation. So deforestation and swamp drainage were blamed for a deterioration of the climate within the span of historical memory in several areas, above all Bohemia, the Hungarian plains, and the karst regions of Carniola, Dalmatia, Croatia, and Bosnia, Bosnia being the last acquired Habsburg colony. Everywhere it was argued that restoring forests would create a moister, more fertile climate. Inquiries into suspected climatic shifts in the course of human history were therefore highly public and politically fraught. In all these ways, climatology's history in Austria sheds light on the science's close ties to 19th century imperialism more generally. At the same time, I argue that the scientific institutions of the Habsburg state formed a unique lens onto the natural world. To see why, we need to recognize the predicament that the Habsburgs found themselves in circa 1800. Now, this dynasty had traditionally justified its rule as divinely ordained, portraying their lands as the fulfillment of the medieval dream of universal empire, as the, quote, bulwark of Christendom against the, quote unquote, Ottoman infidels, and as a mediator between West and East. These arguments all faltered with the waning of the Ottoman threat to Europe in the 18th century. Thereafter, the Habsburgs styled themselves as patrons of the arts and sciences, as incubators of enlightenment, and most ambitiously and significantly for our purposes, as the protectors of the panoply of cultures under their rule. This ideology of unity in diversity proved decisive for the field sciences in Central Europe. So I'm arguing that a decisive feature of modern climate science, its integration of multiple scales, arose in part as a solution to a problem of representation, a problem that engaged Habsburg scientists in particular as servants of a supranational state, right? A state that stood above the multiple nations within it. In a nutshell, the problem was to represent local differences while producing a coherent overview. That is, to do justice to the vaunted diversity of the Habsburg lands, natural and human, while reinforcing the impression of unity. This problem was worked out at the interface between physical and human geography, and it stimulated technical innovations across a range of media, all of which I discuss in my book, from cartography to landscape painting to fiction and poetry and political rhetoric and, of course, mathematical physics. So let me illustrate this representational challenge by means of a few maps. Geography was one among several disciplines that aimed to survey the celebrated diversity of the Habsburg lands and to present its findings to the public. To this end, Habsburg geography was in search of new visual techniques. How could a representation of this territory produce an impression of overarching coherence while highlighting small-scale variability? One famous solution to this problem is Carl von Schönig's ethnographic map of Austria and Hungary. As you see here, it applied stark color contrasts in order to make the visual argument that the ethnic diversity of the monarchy reached down to such minute dimensions that no division of this territory along national lines was conceivable. an analogous problem arose in physical geography. How could a single map represent elevation in a way that would do justice both to the topographical extremes of the Alps and the subtle gradations of the Hungarian flatlands? If we turn now to climatological maps, we're going to find much the same problem as you see here. Since mountains generate strictly local variations of climate. At the time, the most common approach to mapping climate was by means of isotherms, lines connecting points of equal temperature as empirically measured. In order to draw isotherms, scientists would first standardize thermometer readings by correcting for the local elevation, assuming a uniform fall in temperature with height. But this procedure would have obscured some of the variability that Habsburg scientists wished to make visible. Enough with isotherms, one of them exclaimed. So, what to do instead? One innovative alternative, shown here, was to use a spectrum of colors to map a range of warmer to cooler areas based on actual measured values without reduction to sea level. So here, blue represents coolest temperatures. What a map like this revealed was that the more important geographical influence on temperature was not absolute height, but the relative height of mountains with respect to valleys. In other words, this map began to make visible climate dynamics, specifically how the form of the Earth's surface modifies atmospheric motions. Actually, Habsburg scientists fell into dispute with colleagues elsewhere over this technique. So, for instance, this map produced in Vienna of January isotherms depicts, as you can see over here, an extreme cold island in Siberia, characteristic of valleys during anticyclonic conditions. Now, the Russian climatologist Alexander Voykov objected that what was pictured here was an illusion, since the air in the mountains was significantly warmer than in the valleys when anticyclonic conditions prevailed. The Austrian climatologist Julius Hahn disagreed, seeing this cold island as a genuine feature of the climate and insisting that valley temperatures were those most relevant to human life and so deserved to be pictured on the map. So here, Hahn was setting out to visualize climate dynamics in order to communicate the local and practical significance of atmospheric measurements. Here's another example of a technique for visualizing difference, a map of the distribution of days with storms. Now, earlier maps of storm distribution had tabulated stations reporting the same number of storms, then divided Europe rather crudely into regions of summer storms, winter storms, and in the east, a region without winter storms. This map was constructed along entirely different lines. It revealed local contrasts that were obscured by the older method. By keeping local variations in focus, this map makes visible the dynamics of storm generation, not merely their frequency. Namely, it reveals the influence of topography on storms. So, as you can see here, for instance, Vienna displays a greater storm frequency than Wiener Neustadt over here because circular valleys open to the south are more prone to storms than their surroundings. So you may be wondering, why is it that Habsburg scientists were so fixated on details like these? Were they, as the historian Spencer Weir has charged, mere drudges? Consider, for instance, that the director of Vienna's Imperial Royal Central Institute for Meteorology in Vienna once admitted that he had spent a week deciding whether to adjust the average pressure at a single location by 1/10 of a millimeter. Quote, "Many may well wonder if it is even worthy of a serious man to devote so much time and effort to such a minor result." In his defense, he cited no less a historical figure than Francis Bacon. Bacon had once remarked that the natural philosopher who neglects details is like a haughty prince who ignores the petition of a poor woman. He who will not attend to things like these as being too paltry and minute can neither win the kingdom of heaven nor govern it. And I'll point out that this scientist was actually echoing the Emperor Franz I in an earlier statement about his own detailed knowledge of his lands. Now, the Baconian metaphor of the empire of nature is revealing. It underscored the affinity of this scientific precept with the logic of the Habsburg state. Okay, so let me explain what I mean by that. The revolutions of 1848 to 49 had impressed on Habsburg civil servants, like professors, the political significance of modern nationalism. In response, they began to articulate a new ideology of supranationalism, an Austrian idea to replace the outmoded notion of Austria as the bulwark of Christendom. In the famous words of the liberal statesman Adrian Verberg, this alone can be Austria's immediate goal, the preservation of provincial differences, without harm to the unity of the whole. It was in the 1848 era that a new class of scientists emerged, what I refer to as imperial royal scientists, experts on the vast territory of the Habsburg Empire as a whole. Now, the phrase imperial royal, Kaiserlich, Königlich, KK, as it was often abbreviated in front of the names of all imperial institutions, gave rise to the novelist Robert Musil's nickname for the Habsburg monarchy, KK, in German KK. Musil called it Kakania, essentially Pupuland. So, over the following decade after 1848, the imperial royal scientist attained mythic status in the fiction of Adalbert Stifter. Now, Stifter is to Austria what Pushkin is to Russia or Goethe to Germany. And Stifter highlighted the naturalist's capacity. Stifter was actually a failed physicist himself. In his very famous, beloved novel, Indian Summer, he highlighted the naturalist's capacity to assess phenomena according to a more enduring scale than mere personal inclination. So in this novel, the education of the protagonist, a budding naturalist, can be measured by a shift in his perception of scale, his growing attention to nature's signs on the small scale. And towards the end of the novel, he thanks his mentor for lessons in this way of observing, which he says have succeeded in reversing his own sense of scale. The large is small to me, he says, and the small is large. So my book argues that Habsburg field scientists built their public authority on their capacity to set local details in appropriate relation to a synthetic overview, to attend to minutiae without losing sight of the coherence of the whole. It was this ability to judge rightly the significance of small things that gave a science like climatology its political resonance in the decades following the revolutions of 1848. And these political conditions proved fertile for climatology. Working without the aid of digital computers, Habsburg scientists invented creative ways to detect, model, and represent atmospheric motions at multiple scales. These included turning plants into measuring instruments, imagining riverbeds as models of atmospheric waves, and inventing new literary and cartographic genres like the climatography. Although you may not have heard their names before, their ingenuity was widely celebrated in their own day. Their leader, Julius Hahn, was nominated for a Nobel Prize in 1910, and his publications were said by an American colleague to, quote, tower over other books as the pyramids of Giza tower over the valley of the Nile. Others have observed that the research of Hahn and his colleagues was eclectic, in the sense that most climate scientists today specialize at one scale or another, but many of these Habsburg scientists studied phenomena at the planetary scale down to the dimensions of agriculture and human health. And I would emphasize that these were not disconnected investigations. These scientists sought to track the interactions between phenomena at these different scales. To this end, they developed key tools of modern climate science, of which I want to highlight three. The first is small-scale fluid models of atmospheric motion. How many of you are familiar with the rotating dishpan experiment pictured here on the left? Fascinating. So the idea is you fill a vat with fluid and you place a block of ice at the center to simulate the pole, and you could heat the rim to simulate the equator, just rely on the existing temperature differential. And when you set it on a turntable, you see the formation of these whirls that mimic cyclones. So that was invented in the early 20s in Vienna. On the right, you have images of a squall modeled by the sudden mixing of fluids of different densities in a long glass trough. And I'll just note that today, at a time when climate models have grown so staggeringly complex that even experts can't understand their operation at an intuitive level, this is something that Isaac Held has remarked on, these laboratory models of whirling atmospheres remind us of what computation alone cannot achieve. A second key tool invented in the Habsburg world is a measure of the energy available in the atmosphere to generate motion, what's known as APE, or available potential energy, which played an important part in the early general circulation models of the 1960s and 70s and remains important to the analysis of the instability associated with regions of sudden, where temperature varies abruptly, or baroclinic zones. A third key tool was a quantitative measure of turbulent motion applicable to flows of any dimensions. It's called Austausch, the German for exchange. And this concept of exchange opened up two directions for research at once. First, when applied to movements of air perpendicular to the ground, it was of great practical value for characterizing a local climate, for instance, for agricultural purposes, or to think about the dispersion of pollution. But Austausch was equally applicable to studies at the hemispheric scale when looked at in terms of horizontal exchange. It made it possible to quantify turbulent exchange between the equator and the poles. So this research tradition transformed the very meaning of climate. Previously, throughout much of the 19th century, understood as regional in scope, climate became a concept applicable at multiple scales, right, from the local up to the planetary. As late as 1895, in the definitions of the renowned Prussian meteorologist Vladimir Köppen, famous for one of the first worldwide climate maps, the general circulation had marked the limit where climatology edged into meteorology, right? So climatology, Köppen was saying, could not be applied at the global scale. In showing how to apply a climatological tool like Austausch on the scale of the atmosphere as a whole, Habsburg scientists identified the general circulation as an object of climatological research. Indeed, they gave substance to the notion of the planetary climate, the Weltklima. The story I've sketched here today of the rise of dynamic climatology in the Habsburg world is just one small piece of what I would like to envision as a new history of climate knowledge in the broadest sense. A suitably deep, broad, and polyvocal history will have to be a collaborative project. It will require anthropologists as well as historians with expertise in the widest possible range of languages and cultures, working closely with scientists, not only in atmospheric physics, but also in fields like botany, ecology, and geology. And it will require creative ways to convey the interrelations among these various historical strands of knowledge production, in much the same way as Habsburg scientists invented new genres to represent unity in diversity without masking difference. Thank you. And I'll just add, as Amity mentioned, some of you may see me as a student in your classrooms next year. And so I really do mean this presentation as an invitation for input, including what I should be studying, and as an invitation to collaboration in the sense that I really do see this project of writing a much more capacious history of climate knowledge as fundamentally collaborative. So I welcome questions and comments.
I was curious if you could comment on the connection between the emergent climate science and also the emergent science of ethnology, and the way that climate scientists might have sort of imagined that factoring into sort of the project of human difference in ruling subjects.
Yeah, so I see these as very closely linked, and the historical actors did too. Climatologists often noted that a traveler making records of climate in a foreign land should also be noting ethnographic features, what kind of crops were grown, what various customs could give clues to local climates as you were passing through a region. So being an ethnographer and being a climatologist often involve the same kinds of observations. I think in terms of the representation of difference, right, these are also tightly connected. So some of the maps I was showing you come from the Atlas of Austria-Hungary that was published in the 1880s that began with climate maps, sending the message that climate is the fundamental variable, moved on to other elements of the natural world like forest cover, hydrology, and then the second half was statistical, as the term was, demographic, we would say, including actual ethnic maps, which were usually linguistically based. That was the way the data was gathered in the Habsburg world. And to this range of maps, many of the same conventions were applied, right? So that the message was made was sent very, very clearly that you could not understand the ethnographic distribution without understanding the distribution of climate. Do you want to go?
I mean, you have the Habsburg Empire, and because they're growing their empire, they needed to understand, the climate throughout the entire region that led to the science. But you've had other empires build, and so what is the sort of confluence of events that led to a formal science emerging? Why didn't the Romans do it, or the Ottomans even? Why, or the Chinese, or did the Chinese do it? Or like, how do you isolate or identify where sort of this ground zero is as a historian?
Yeah, I wish I knew. I mean, that's part of why I'm here to say I need help, because I don't have the resources to study climatology in the ancient Roman Empire, the Ottoman Empire, or China's empires. I would love to work with people who do have access to that history. What I have done is to look comparatively, to the extent possible, given the secondary sources, at the modern European overseas empires and the continental empires, right, of the same period, which includes the Ottomans. And I think one key difference that you see is that the continuity of landmass mattered a great deal for the study of climatology. The Brits could not make sense of their kind of scattered meteorological knowledge because there were these vast oceans, right, separating their measurements. But then when you compare the Habsburg Empire to particularly the Russian Empire, the other great land empire of the time, you see actually a great deal of similarity. The Russians were also pursuing small-scale climatology, agricultural climatology, in much the same ways, for much the same reasons that the Habsburgs were. I think the real difference is that it didn't have the ideological cachet. Because, I mean, so you see this in that the Russian state was not interested in the local studies. The Habsburg state cultivated study at the local level. They really intended to move back and forth between that kind of provincial, local research and the more abstract, theoretical, global project. You don't see that kind of dialogue in the Russian case.
Deb, thank you so much. Extraordinary amount of research here. Two questions. One, you've referred to the Little Ice Age, and I was wondering about the consciousness of that in Europe. And the second question is the consciousness of evolution as part of this that was emerging in the 19th century, and how might that overlap with your research?
Okay, so those are really big questions. I feel like I can only touch on them. Excellent questions. So, consciousness of the Little Ice Age. So I showed you, actually, I think the poster for my talk included an image by Friedrich Simony, one of the great physical geographers of glacier phenomena. These scientists were measuring the retreat of the glaciers. So by 1900, you have that record. Simony actually has photographs of individual glaciers where you can actually measure the retreat. But for the most part, there was a lot of confusion about what kind of climate change these people might have been living through. You know, as I said, they were very concerned about the desiccation of the climate, particularly in certain regions, and quick to blame human activity for what they perceived as a drier climate. There were many attempts to muster evidence for that desiccation on the basis of historical records, on the basis of experiment. This was all very inconclusive. So I would say that, basically, in terms of climate change on the historical timescale, there was just confusion. So the question about evolution is obviously tied, and one of the ways in which one scientist really in particular, tried to make sense of climate change on the historical timescale was, as I've hinted, by using plants as climate measuring instruments and tracking changes in the distribution of species over time. So kind of adding a temporal dimension to botanical geography, which is often celebrated today as the precursor of ecology, in the 19th century. And I think it hasn't been appreciated the degree to which botanical geography was also concerned with mapping climate change over time, at least in this world.
How it affected the progress of this field, whether there was enough inertia that some of the same ideas kept moving forward, or whether the end sort of things splintered off from there.
Yeah, that's an excellent historical question. And, there are continuities and discontinuities. One of the things that is a striking continuity is the pursuit of small-scale climatology. So the Austrians were among the pioneers of the field of microclimatology already in the imperial period. But they really push ahead. Not just, right? And so when we're talking about post-1918, we're talking about multiple nation states. The First Republic of Austria and the Republic of Czechoslovakia turn out to be really the world leaders in this new field of microclimatology. Actually comes to be called bioclimatology in the 1930s. So that's a really interesting thread of continuity. I think the major discontinuity, and it's really, really gives the historian pause, is that some of the same tropes of kind of unity and diversity, and much of the same data, after 1918 is being used to support a fairly patently racist German imperialism. And you see this through the Nazi era, and even some of the former, essentially Nazis who managed to hang on to power into the post-World War II period, continue to use those same tropes, of the Austria being, right, this multiplicity that has, some kind of natural unity, but now they need it in, I think, an entirely different way than it was meant in the imperial period.
Thank you. Hello, thank you for your talk. Sorry. I'd like to ask you about the role of German and British scientists in the exploration of Patagonia, where maybe it's not directly related, but I wonder if this is like a soft power imperialisms, or there was just like serving those governments in Argentina and Chile?
I'm sorry, it's not something I've looked into. I would be curious to talk with you more after. And I'm not, so I wouldn't want to confuse Austrian and German researchers. Yeah.
Thank you. Thanks for your talk. It's an area of the world I really know very little about. Under the concept of history, we're supposed to learn from history. That is, not repeat our mistakes, that kind of naive view of what a historian might provide. How do you relate your thinking, and it doesn't have to be from this talk, to how we should be interpreting today? I don't really know the topic. You can pick anything you want. I'm sure there are a lot of topics, but it's more of a question to you as a historian, really, than particularly about this talk.
Yeah, I think about this a lot. What does history have to teach us in this moment of great need? One of the things that I feel I understand better by virtue of my historical research is what motivates members of the public to engage with science. So my last book was actually about seismology as a citizen science in the 19th century, and the communication between citizens and seismologists about earthquakes, big and small. And so I think that there's a level of personal contact that really got ordinary people excited about being involved in contributing to a science. And so I'm really interested in, optimistic about citizen science initiatives today. What concerns me is when they seem to be a little bit about show rather than substance. Because I think people can tell. I think people in the 19th century, they wanted to receive the publications that included their evidence, right, in the footnotes. And so I think the public can tell when they're doing busy work that's not actually feeding into science. So I think, citizen science, what's now today called citizen science, has been a huge part of science in the past, right? Before strict professionalization, before networks of measuring instruments. And so I think in terms of public participation and public communication, there's a huge amount that we can learn from history. Yeah. Yep, that's basically my guess about what happened in the 20th century, and that's part of where I want to go next, is understanding how that happened. And I think as I've talked about just a bit with Karen, I suspect it has something to do with the way the field of geography fell apart. That makes sense.
Hi, over here. Thank you so much for your fascinating talk. I really enjoyed it. Can you say a little bit more about how these Royal Imperial scientists were developing the expertise at the local level? And what I mean by that is, were they doing a lot of field work? Were they essentially corralling a bunch of farmers or other sorts of, artisans, people who knew about local climates, people who knew that, okay, we can set up like a weather station here behind this valley, people who had that local knowledge about the local geography or local climate, essentially. And so how is that relationship, how is it happening? Do we have evidence of that?
Yeah, plenty of evidence, and the answer is both ways. So as I was mentioning and talking about citizen science, networks of observers were cultivated and really actively cultivated. Scientists went way out of their way to appeal to the public, to take part in observation and measurement. There were instruments widely distributed, and scientists in Vienna regularly made treks around the empire to make sure that the instruments were calibrated against each other. At the same time, it was very important, really to win the authority of an imperial royal scientist, right? And that was really to reach the epitome of scientific authority. One needed to demonstrate a kind of embodied knowledge of the territory of the empire. And so you have scientists, going off on these field trips, writing about them. It was also a mode of socialization. It was a rite of passage, and there was a way in which this was an embodied form of knowledge and a gendered and sexualized form of knowledge.
Thanks so much for this very challenging set of observations. What I find particularly intriguing is the standard notion that British, Swiss, and German geologists in the early 19th century, as opposed to the Austro-Hungarians, that British, Swiss, and German geologists were actually discovering Earth system history. And this was not really the paradigm of the Austro-Hungarian Empire scientists. That really dynamic climatology begins with the observation that there was a glacial age, the Pleistocene, which is succeeded by the Holocene. And this was really Charles Lyell and Gunz, Mendel, Ries, and Wood working in the Alps, defining glacial expansion and recession. I think the Austro-Hungarians might have been in the background, not in the foreground, in that set of very crucial observations.
Yeah, so the Ice Age research that you're describing is certainly crucial to modern climate science. I wouldn't call it dynamic climatology, right? So my definition of dynamic climatology emphasizes the application of thermodynamics and fluid mechanics to the atmosphere. Obviously, these guys were not doing that. So it's another piece of the puzzle, but I suppose I would argue that it's not modern by my own definition. Only a little.
Okay. Yeah, we were just reflecting on how some of the readings we had done for his class trace back to like the 5th century, the 1700s and 1300s across different societies and cultures with Hippocrates, Ibn Khaldun, and Montesquieu. So I don't know, just as I'd be happy to chat after or share the syllabus. Yeah. Okay, thank you.